All right, question 1 shows these box plots of gas mileage for cars manufactured in 2 different countries. And so we're going to look at these distributions and talk about them a little bit. Part A says to compare distributions for the cars manufactured in country A and the sample in country B. So whenever we're asked to compare distributions, we're going to start by making sure that we are using comparison language when we talk about shape, center, spread, and outliers. So you'll notice that we don't just list out the values, we actually directly use comparison words like greater than, less than, about the same. So for our comparison in part A, country A has a high-end outlier at around 38 miles per gallon, while country B's distribution has no outliers. So we're comparing the fact that A has outliers and B does not. The cars from country A have a lower median, there's that comparison word, lower median, which is at 18, than the cars from country B. And then A has a lower IQR than country B's IQR. So we're comparing center, we're comparing spread. We're also talking about one having an outlier and one not having an outlier. In part B, this is testing your knowledge of our measures of center. Would we expect the mean to be greater than 18, less than 18, or equal to 18? Well, since the median is at 18 for country A, we already talked about that, we want to look at the shape and measure of outliers because remember the mean is not a resistant measure to those. So we're going to say that the mean is going to be greater. That's because our shape looks to be slightly skewed to the right from the box plot. And there's also an outlier on the high end. And remember, the means formula will add up all the values, including those higher end values from the skewness, including the outlier. Whereas the median is just interested in that middle value. So that mean gets pulled to the right by those higher values from the skewness and the outliers. In part C, we're going to make a new box plot that combines these 2 different data sets. First part asks, what is the range of the combined data set? Well, if I put both of the sets of data together, then my highest end is going to be at the 40. My lowest end is going to be at the 14. So the maximum comes from country B and the minimum comes from country A. And so that will determine my range, which is 40 minus 14, which is 26. Then it asks, where would we expect the median to be? Well, remember, the median is the middle data point. So if there's 200 values, we would expect it to be around the 100th data point. And we can actually determine where the 100th data point is because the box plot splits us nicely into little quartiles. So we can go ahead and say, well, we have from here to the left, we have 75 values right here. And then from 24 to the left, we have 25 values. And then we can make the same argument the other way, that we'll have 25 above from country A and 75 above from country B. Therefore, we're going to say the median is at 24. Based on the quartiles, 24 should be the median because 100 data points are below 24, 75 of them from A and 25 of them from B. And then 100 of them are above 24, 25 of them from A, 75 from B. On to question 2, which is our question about experimental design. So in question 2, they give you the farm plots. They also say that we believe that the aphid damage is greater for the regions that are closer to the river. That's going to be important. And then they lay out these 3 methods. One is basically a convenience sample. One tries to be, one of them tries to be basically a cluster sample, and one basically tries to be a stratified sample. So it asks for method 1, are we good to just select region 3, which is closest to the house, farthest away from the river? Probably not. That's a convenience sample. So some problems with that is that we are not going to have an accurate estimate. Region 3 is the one that's furthest away from the river. It wasn't selected randomly. It was handpicked out. It's closest to the farmer's house, so it's the easiest one to look after. So method 1 will probably underestimate that proportion of the damage. Whereas method 2, going to part B, method 2 will probably be overestimating. The reason that is because they select row E. And remember, row E is closest to the river, which we think will have greater amount of damage. So method 2 will likely overestimate this proportion since row E is closest to the river, and it's believed those regions are more susceptible to the damage. Therefore, and only those regions are being sampled, so we're saying that it's going to overestimate. Now part C asks about method 3, which is a better method, that stratified sample, and it asks us to walk through how we would do that, how we would use that method. So, first thing we're going to do, we're going to use a random number generator to select 5 random numbers. I'm going to go 1 to 5. Now the important thing is that we want to do this with replacement. So we are going to use repeats in using this method. So each digit is going to determine which column from that row we're going to use. So the first digit tells me what we're going to use from row A, the second digit from row B, and so on. So for example, for the fourth digit, if that fourth digit is a 3, we'll use the region in row D from the third column, which is 18. So we look at row D, it gives us a 3, and so we go 1, 2, 3. Here is the region that we're going to use. So each of the numbers will tell us a number from the region to use. Now, there are other ways. You don't have to use a random number generator. You could use a table of digits. You could roll a die and say you're going to ignore the 6. That would give you 5 outcomes. You could do 5 different colored chips with replacement. You can use random numbers instead of using 1 to 5 each time. You could pick a random number from 1 to 5, and then a random number from 6 to 10, and then a random number from 11 through 15. You can use random INT in the calculator. You can talk about slips of paper. If you're doing slips of paper, you should either be doing it with replacement or like this method that use the different groups of numbers, you could group them in different hats and go through it that way. But the process needs to have 5 digits or 5 outcomes that you're selecting from each time, and that will correspond to each of the rows. That's the idea that they want you to do on that one. On to number 3. Now, number 3 is your probability question. So question 3 is probability. And we are going to be looking at a digital playlist that we're playing from. And we are looking at rock songs, selecting rock songs each time. So suppose a song is selected at random to be played. What's the probability that the song is a rock song? Well, we're told what the distribution looks like. We got 1,000 songs, and it's with replacement. It's that any song can be played at any time, and there can be repeats. So we are doing it with replacement. So for rock songs, well, there's 100 rock songs out of the 1,000, so 0.1. And the probability that we pick 2 rock songs, well, there can be repeats. So it's 0.1 times the 0.1 to make 0.01. Part B, we have 20 songs that we're playing in a 1-hour period, and we're interested in how many of the songs are rock songs out of those 20 songs in that 1-hour period. Well, let's define the variable. Let's make sure we define the variable. The variable is the number of songs that are played in the 1-hour period that are rock songs. How many of the songs are rock songs? And that is going to follow a binomial distribution. And anytime we talk about a binomial distribution, we should talk about what is n, what is p. Well, n, our number of trials, is how many songs are getting played in total. That's 20. And then p is our probability of the thing happening. So the probability that we get a rock song, which, as we saw in part A, was 0.1. Then it asks, what is expected value? Well, since it's binomial distribution, the expected value, the mean, is n times p. So 1/10 of those 20 songs, which is 2, is how many we would expect on average to be rock songs over the course of many of these 20 song cycles. Part C. We still have our same distribution, and we say, what is the probability that 4 or more songs that are played are rock songs? So we want the probability that x is at least 4. So we would add up from 20 choose 4 times, we want it to happen 4 times and not happen 16 times, all the way up to 20. Now, if you're doing it in the calculator, remember that the binomial CDF is less than or equal to. So the opposite of it happening 4 or more times is it happening 3 or fewer times. So we're going to use CDF, and our x value is going to equal 3. And we're going to go 1 minus that opposite of it happening 3 or fewer times. Either way, you get 0.1330. And then it asks, well, does that mean that it's unlikely that this happened at random? Well, that probability of hearing at least 4 rock songs is not unreasonably small. So we're not going to conclude that the process was not truly random, because there's reasonable likelihood that this could have happened by chance. You'll notice I didn't talk about a p-value because it specifically asked us to not do an inference procedure. So we're not doing a hypothesis test here. We're just basing it on this probability. And is that probability or likelihood enough to disqualify? No, it's not. But our inference procedure is happening in question 4. So we've got our application that can help with homework. We have 22% of high school students in the country use it, and we want to know if the proportion that use it is greater than the proportion for the country. So we've got 130 students, there's our n, and then 38 is our x value. So this will give us our p hat. So you'll notice that it's a 1 proportion, because we are looking at this 1 proportion and comparing it to the national amount. So our null hypothesis is that p is the 0.22 that we got from the country. The alternative is that p is greater than 0.22. We're using an alpha level of 0.05. That's what the problem told us to use. And I went ahead and put the p hat in there. So p is the proportion of all the students in her high school that use the app to help them with homework at least once a week. So this is a 1 proportion z-test, or a 1 sample z-test for proportions. And we're going to check our conditions, our usual conditions. So we have a random sample of 130 students from the high school. So that's our random condition met. For normal, remember we use p naught. We're assuming that the null is true. So we're looking at that distribution. So that's why we're using the 0.22 there. So 130 times the 0.22, 130 times the 1 minus 0.22, both are at least 10. So we can approximate a normal distribution. And then for independence, we take 10 times our sample size of 1,300. Is that smaller than the population? Well, the population is a high school with more than 2,000 students. So therefore, we can assume independence. So then we go into our formula for the z-score. Here's the only place that p hat gets used. P hat minus our value of p naught over our standard deviation. And again, p naught is in the denominator there because we're assuming the null is true. That's the distribution we're using. And we get a z-score of 1.99. And our p-value based on that z-score is 0.0233, which is less than our alpha level. That means we're going to reject the null hypothesis, smaller than that alpha level, which means there is enough evidence for the alternative, which is that that proportion that used that app is greater than 0.22. So that's the results of our hypothesis test. We ended up rejecting, and you're going to see that rejection sentence happen again in the next couple of problems. On number 5, we have a table giving the distribution of bedrooms that were sampled in 2024. And eventually, we're going to look to compare it to the number of bedrooms in 2017. So, starting with part A, we have this table, and we're going to select a house at random. What is the probability that the house had fewer than 3 bedrooms? And then the next part asks, what is the mean? So, if we want the probability that we have fewer than 3, well, fewer than 3 means either 2 or 1. So 2 or 1, or means we're going to add them together to get 0.34. And then the mean, well, we're going to use expected value, which is value times probability of it happening, and add them together to get a total of 3.1 bedrooms. That is our mean that we are looking at on part A. Now, once we have that mean, part B says we're going to use a one sample t-test for the mean to test the belief. So we're going to state the hypotheses and then talk about what a type 1 error would be. So it says we are looking at comparing it to 2017, and it just says we want to know if there has been a change, if there is a difference. So it does not give a particular direction. That means our alternative is going to be that the mean is not equal to the 2.9. And we're using 2.9 because that's what it was in 2017. So our null is that the mean is 2.9. Our alternative is that the mean is not 2.9. And mu is the mean number of bedrooms in 2024. Then we're asked what a type 1 error is. A type 1 error in this context would be rejecting incorrectly. So if we're rejecting, that means we're concluding that the mean number is different from 2.9 when it actually is 2.9. So that would be rejecting, concluding that that mean is different from 2.9, but we're doing it incorrectly, so it actually is 2.9. Then over in part C, it gives a confidence interval. And that confidence interval is 3.01 to 3.19. And we look at that confidence interval, that 97% confidence interval, and we look at the fact that 2.9 is not in that confidence interval. Since 2.9 is not included in the 97% confidence interval, that gives us our conclusion of the two-sided test at a 0.03 alpha level. And since it's not in the interval, we're going to reject the null hypothesis at the 0.03 alpha level. There is enough evidence to say that the mean number of bedrooms is different from the 2.9, from what it was in 2017. Finally, question 6. In question 6, we've got 2 separate samples that we're looking at of the 50 children. One is going to do the reading in the morning, and one is going to do the reading in the afternoon. The way that this question tries to kind of overwhelm us is with a whole bunch of information and a whole bunch of new formulas, but we're not going to get overwhelmed. In part A, we've got our p-value of 0.002. So we're going to state the appropriate conclusion of that hypothesis test and say that p-value is less than any alpha level we would reasonably give. Therefore, we're going to reject the null hypothesis. There is enough evidence to conclude that the scores are different at 9 a.m. than they are at 3 p.m. In part B, It asks, well, they used a two-sample t-test instead of a paired t-test. So why did they do that? Well, the reason they did that is because the data was not paired. It was two separate independent samples that we are comparing with each other. So they were not paired off in any particular way. The two samples are completely separate. If we wanted to pair them, we could pair them by like the top reading scores, the top two kind of pre-test reading scores, and then pair those data together and randomly assign one to one treatment and one to the other, and then so on. Or we could have the same person act as their own pair, and they read one passage at 9 a.m. and then read a separate passage at 3 p.m. and then do the testing from there. So not paired off in any way. In part C, again, here's the big block of text, but the short version is that we've got this coefficient that will talk to us about how much practical importance the p-value has. Because if you remember, we have looked at cases where statistical significance does not mean that it actually has any practical meaning. So rejecting the null hypothesis doesn't mean that it actually carries any weight, especially if you have a large sample size. The large sample sizes can detect very, very tiny differences. And sometimes those tiny differences don't actually have any practical importance. So a way that we are doing that is with this D coefficient. So what I did was I calculated S sub p separately. And again, we're using the values from the table up here. So for S sub p, we take our standard deviations, square them, add them together, divide by 2, and then put them under square root. And then that's going to go in the denominator of D. So absolute value of the difference of the means divided by that S sub p gives us 0.6312. And we're going to interpret that based on this chart that they give us. And 0.6312, well, that falls right in this region right here, which would be somewhat meaningful in real life. So this value is between 0.2 and 0.8. The difference in the scores is somewhat meaningful in real life. And then finally, in part D, it says, let's take these and increase the standard deviation to both be greater than 4.43. Would that bring the coefficient up, down, or keep it the same? Well, if standard deviation goes up, then that means S sub p is going to go up. So that will make the denominator larger. And if we make the denominator larger, that makes the overall value smaller. And if the overall value is smaller, that gives it less practical importance to real life, but probably not enough to change the classification that we gave of somewhat meaningful. It's got to go down quite a bit more before we actually say that it's less meaningful. In fact, if you do some calculations in this, you don't have to, but if you do, then you'll find that changing them both to be a little bit bigger than 4.43 brings it down from 0.63 to not even below 0.6. So it's going to be hard for it to change its rating in the actual table to say that all the way down to the next classification. So overall, fairly straightforward set, especially if you don't get overwhelmed by the big blocks of text in question 6.